So here we are, lesson 8.2 of the 214 part of the course, and we're going to learn about logic and logical arguments. In the previous section, we had the example where Fluffy is a cat, and the diagram here shows Fluffy the cat, and Fluffy must be an animal. We do not want to bring in any previous knowledge or anything else, just what we're told about Fluffy. So we can write a conclusion of a logical argument. So we can write this conclusion as, meaning we can take this diagram and conclude something about it. So we can use our Euler diagram to write a logical argument and then come to a conclusion about it. So let's see. We have all cats are animals and Fluffy is a cat. And the first one, all cats are animals, we call premise 1. And Fluffy is a cat, we call premise 2. And the first two lines of the arguments of these premises are things that we take to be true. The last line here is the conclusion. And as you see, it's not part of the diagram. We just use the diagram to analyze and find a conclusion. And we call this particular type of argument valid because it turns out that Fluffy, here, Fluffy the cat, is only in one place. But what would we do if the argument is not valid? Well, let's try a slightly different set of premises and conclusion. So here we go. So we have all cats are animals. Dan is an animal, therefore Dan is a cat. So, well, Dan is an animal. All cats are animals, okay. And Dan is an animal. Well, Dan can be an animal cat, or Dan can be some other kind of animal like a human being. So we can put the D for Dan in both places. We can put him either as an animal cat, which is fine, or we can put him as just an animal. It's not particular what kind of animal. He could be a cat. He may not be a cat. We're not given explicitly what kind of animal he is. And the conclusion, based on the conclusion that we're given, therefore Dan is a cat. Well, this is not a valid argument because we can place the D for Dan in two different places, and that would mean that this is not a valid argument. Looking at example 1, we're going to decide which conclusion is valid. So let's see. We have a situation, premise 1, all squares are four-sided. M is four-sided, therefore M is a square. And here we have all squares are four-sided. X is a square, therefore X is four-sided. So we're going to use the premises to make our Euler diagram, and then we're going to place our M or our X to see if the conclusion is valid or not. So let's try this. Now remember, we only use the premises to make the diagram, not the conclusion. So here, let's do it. So here we draw our Euler diagram, and here we have our two arguments with their premises. So let's look at how we do this. We have in the larger circle, we have four-sided things because that's more general, and squares are a particular kind of four-sided thing. So remember, this is a four-sided thing, but it's not a square, but squares, again, are a particular kind of four-sided thing. So, let's look at the first premise in this one. All squares are four-sided. Okay, so here, and M is four-sided. So that means M is four-sided, so it may be a square. That's true. And it may not be a square, but still it's four-sided. So it could be either this guy over here, a parallelogram, or a trapezoid, or M could be a square, which is still four-sided. It's sort of not clear whether M should fall only here or only here. Well, let's look at the other argument. All squares are four-sided. Okay, that's all right. And X is a square. So that means X can only be here. So thus, it turns out that our conclusion, the only one that is true is this one, because it falls in one place in the Euler diagram, and this one is not valid because M falls in two places. So X falls in one place, that means this is valid, and M falls in two places, that means this argument is not valid. Another way to show a logical argument is to use, instead of an Euler diagram or with an Euler diagram, we're going to use symbols. So, all cats are animals is the same thing as saying, if it is a cat, then it is an animal. This is called an if-then statement. And an if-then statement is known as the conditional in logic language. And we use the arrow to represent conditional. If it is C, then it is A. Where C is it is a cat and A is it is an animal. And then for the conclusion, we use 3 dots for the word therefore. So let's look at our first argument that we did about Fluffy the cat and now put it more in a symbolic language. So recall that when we were using all cats are animals. Well, we're going to now rewrite it as an if-then statement or using the conditional. If it is a cat, then it is an animal. And then I'm going to take the symbols, if cat, then animal. Now for my second premise. Fluffy is a cat. Now here I'm going to drop the name of the cat, and I'm just going to say it is a cat. So we have here C. And then finally, therefore, Fluffy is an animal. And so that would be, for that original way we had it when we were using the Euler diagram. Now we're just going to write it in the conditional language, therefore it is an animal. And here in symbols, we have the 3 dots, therefore A. So as mentioned, when we go from the all way of writing it to the conditional, we don't use the name of the cat. So the second premise can match the first. And you can see if it is a cat, it is a cat. So there it matches. Let's look at the argument that wasn't valid about Dan. So we start out, we have using the all, using the conditional and symbols. So we start out, all cats are animals. Okay, and then we put it in the conditional language. If it is a cat, then it is an animal. And then symbols, if cat, then animal. Now we add in the second premise about Dan. Dan is an animal. Now using the conditional, we drop the specifics about the name. So we just say it is an animal, and then of course in symbols, just a. And then we have our conclusion, therefore Dan is a cat, therefore it is a cat, and there's the 3 dots, therefore cat. So we want to look at the order of these 2 arguments. And we see that they are if-then statements, and we want to be very, very careful about what's happening here. So let's look more closely at the 2 arguments, the valid one about Fluffy and the invalid one about Dan. So the valid argument, and this is called Modus Ponens, and that's a Latin name, and you don't have to learn the Latin words. You just have to understand what a valid argument is and an invalid one. So let's look at the valid argument, and we see that A goes to B, A goes to B, and we see A to A, and B and B. This is the one that's not the correct order. So when we go A, B, B, that's not the correct order. Where here, A, B, A, that is the correct order. And then the conclusion, therefore B, B, and then therefore A, that's not the correct order. Where this one, when you have therefore B, A, B, and here it's reversed, B, A, then you say, hey, there's something wrong here. So as mentioned, the official name for a valid argument is called Modus Ponens, and that would say, just says the correct order. And a valid argument has the second premise and conclusion that follow the same order that as they are in the conditional statement. So we have A to B, and then B to A. That's invalid. And then in a valid argument, we have A, B, A, B. So here, there's a reversal here that is not good, and here we have A, B, that is good. So let's look at the symbols a little more closely. And here we have the conditional. So here the first thing is A, and the second thing is B, and the first thing happens. And then the conclusion, therefore the second thing must be true, since our premise, the first line, said if the first thing A happens, then B must be true. So these are important things to know when dealing with the conditional statement. So it's important to know how you can tell the pattern of a valid argument and distinguish a valid argument's pattern between an invalid argument's pattern. In example number 2, we're going to decide whether or not this following argument about Bonzo is valid or invalid. We are first going to look at the argument using an Euler diagram and then use symbolic logic. So, all dogs are friendly, Bonzo is a dog, and therefore Bonzo is friendly. Well, in order to construct the Euler diagram, we're going to use the first 2 premises. So we construct the diagram as follows. friendly things for all the friendly things, and then we have dogs inside friendly things. And then we see, where does Bonzo fit into it? Well, Bonzo is a friendly thing, and Bonzo is a dog, so therefore we have Bonzo right here. So therefore Bonzo is friendly. Now let's use symbolic logic to make this symbolic logic to see if this verifies what we just did with the Euler diagram or not. So we first write our argument, conditional, and symbols, and we first do the first line, all dogs are friendly. Then we write it in terms of the conditional language, if a dog, then friendly. And then the symbol, dog, if dog, then friendly. Then we have Bonzo is a dog, it's a dog, and then dog. Notice how I just dropped the name, because the name is not so important in the conditional. And then finally our conclusion, therefore Bonzo is friendly. And then for the conditional, therefore it's friendly. And then for the symbolic, therefore friendly. So let's look at the construction of this argument to see that we see that using the symbols, D goes to F and then D goes to F. So that means that since it's going this way, D to F, and then finally D to F, this would indicate that this argument is valid. So we see that it's the correct pattern for a valid argument, and therefore it's also valid when we use symbolic logic. Now let's look at example number 3 and talk about Rex and decide whether or not the following argument is valid or invalid. And again, we're going to start out with Euler diagrams and see if our symbolic logic diagram backs up the Euler diagram. So all dogs are friendly. Rex is friendly. Therefore, Rex is a dog. So we construct our Euler diagram using our first two premises about friendly things and dogs. Well, we see Rex is friendly, so Rex is definitely a friendly thing. And Rex could be a dog, so we'll put him in dog. But the thing is we're not sure whether or not Rex is definitely a dog or not. He's a friendly thing, or she's a friendly thing, but we're not 100% sure, so we can put Rex in friendly things and Rex in dogs. But since Rex can be in two different places, as we've discussed earlier, that means this is an invalid argument. So, therefore, as I said, this is invalid. Now let's check this against our symbolic logic. So here we have the argument, conditional, and symbols, and then we write down all dogs are friendly, if dog, then friendly, and then symbols, if dog, then friendly. And then we have Rex is friendly. In the conditional, we drop the name and just say it's friendly, and then finally friendly, F for friendly. And then lastly, therefore Rex is a dog, therefore it's a dog, therefore D. So let's look at the pattern, D to F, but this goes F to D. This is the wrong order. So because for it to be the right order, it would have to be D to F. but this is the wrong order. Therefore, it is invalid. So we see that it's invalid because we have, as mentioned, the wrong order. The last type of argument that we're going to discuss here is the not symbol in a logical argument, or what it means to be not something. So in logical arguments, if we say it is not a dog, we would use the letter D to mean it's a dog, and then we would put a symbol, a little tilde, in front of it to mean not a dog. This is similar to the complement symbol in sets. So let's look at example number 4. So we're going to look at the following argument and see if it's invalid or valid. So, if it is green, then it is not a dog. It is green. Therefore, it is not a dog. So here, we're going to look at it in terms of a symbolic logical argument. So we're going to have the conditional and the symbols. So we start off, if it's green, then it is not a dog. So if green, then not dog. No dogs are green. We can conclude that there. But that's not technically, so no dogs are green. Then we can say it is green. And that's the conditional, and the symbol green, and then we say Henry is green. Therefore, it is not a dog. So therefore, Henry is not a dog. So let's look at the pattern of the argument. So the argument is valid. And the reason why is because we have the right pattern. So even though we have a not here, the pattern has to be A, not B, and then A, not B. So A, then, if A, then not B, and then A, therefore not B. So notice that the pattern is similar to the conditional. Okay, thank you very much, and stay well. And this is the end of the 214 part of the course. I hope you found this video enjoyable and helpful. Take care. Bye.